with switches, the current that kept going through the conductor, it was now a RL circuit. And you asked us the question, why
so
must we
when we have an arbitrary source, can you literally put in anything?
that's impossible? Which, but you said we should open one.
Wait, what are you talking about?
Right, so it was something like this.
So like, he had a...
Oh,
There's another switch here and then a resistor.
Yes.
And neglecting the status of whether those are open or closed.
No, I mean, if it's an arbitrary source, I guess people...
So this is U1, U2, and initially U1 closed and U2 open.
It's a step function.
Initial state, right?
It's arbitrary.
So that's okay?
And so
Arbitrary.
the question becomes then,
It's a step function.
when you flip, so eventually at some point U2 is closed and U1 is open.
It's a step function. That's what it is. But when it's arbitrary, it's just I/S.
And U1 open. And so how do you do that safely? And so if you think about it, so initially U1 is closed. So here's our initial state, little dot, dot, dot. And then that opens and then this closes. And so how do you do that safely? Well, what's safe operation here? What safety protocols do we have to observe when we have inductors and capacitors? What can we not do?
It suggested that the current in the inductor has somewhere to go.
Right, then that's the solution to this problem. So if we drive the left part of the circuit to DC steady state, we have current through the inductor. If we leave this open and open that switch, what happens? Well, that inductor is still trying to force so many amps or whatever it is through it. And so what happens? Well,
That's for the time.
bad thing supposedly. Depending on the size of the inductor, if it's a big inductor, you'll get serious arcing. And so actually, and I think I mentioned this in class, if this was a real power problem, if you were looking at tens or hundreds of amps through this circuit, you couldn't physically pull this, not by yourself. You need a hydraulic press or something like that to throw this way. So the magnetic field here actually tries to keep it closed, and you're not physically strong enough to open it yourself. So that's the inductor fighting against you. Once you open it, then in that type of situation, you have a catastrophic failure here, but hopefully it prevents catastrophic failure somewhere else. So burning out a good inductor is better than burning out a substation or something like that. Or, a housing development or whatever. There's better failure modes in this, but that's an overview. And so what do you have to do? Well, you close this first, then you open that. So that gives a path for the current to flow. Because you can't do two things simultaneously. It's just impossible. And so close this one first, then open that one. Same thing with capacitors. What can you not do with capacitors? Slightly different scenario. What can't you do with capacitors? So if you have a battery that's a 9-volt battery, you hook it up to a capacitor that's charged to 5 volts, what happens? A lot of excitement for a very quick period of time as you have rapid current discharging the battery. So you can't have a jump discontinuity, or you can't suddenly change the voltage across a capacitor without, I don't know who said it, but without sparking. So you'll have arcs. And again, the arcs are usually large currents and potentially damaging. I don't know if has anybody burned out components in circuits lab yet? Burned out your transistor? Your op amp? Probably not so common in circuits. People in the power lab that I teach, they're doing it left and right. So burn stuff out. Someone in the EI did it by connecting negative power to the positive connection on the transistor and the positive power to the negative connection. So they reverse bias their transistor. The same chip you have, but it didn't like that. So the chip has done that. that wasn't very exciting. There was no heat or anything. There is a, I think we've lost it. It was around for a while. There was a, I think it was a compass from Lec13 that was on the podium for a while. That had a huge divot in it from where someone had shorted the connections through it and dumped a bunch of current through it. Blew the fuse on the car. The chip heated up really fast and developed a nice pit. So, all sorts of bad things you can do. And if they're just chips, they're pennies to replace. If they're power systems, millions to billions of dollars to replace. I don't know what the big power outage we had a few years ago cost me. Does anybody know? You guys, everybody in the Northeast, remember that? You'd have probably been in junior high at the time. That's pretty cool. Billion? No, it had to be more than that. Well, the losses just from things going down had to be. And then we had the ice storm a few years ago. That had to be more expensive. We've had 2 ice storms here. One 3 years ago. It should have been, you were in high school 3 or 4 years ago. You guys remember that? That was pretty cool. I actually had to come into campus and sleep. After 3 days of having no power in my house, I was getting kind of cold. I slept in my lap. It's my shelter. But that was the second one. We had one back in, I think, '97 that was even worse than upstate New York. These get really expensive because they tear down the power lines. And so they have to bring power to do work and then replace all that. And so very, very expensive. So New York said that happened a couple times in the last decade. Anyway, back to circuit stuff. Any other questions on the exam? Everybody feels good? Sufficiently scared? All right, Unit 3 we go. So, Unit 3, now we're back to AC steady state problems. An AC steady state just means sinusoid. So everything's a sinusoidal problem. That's been on since the beginning of time. So the same as DC steady state, everything is the same, except now we have complex numbers. So if you understand that, then you're 2 weeks ahead. So everything's the same. We can do Ohm's law. You know, we've already done it. We've already kept these concepts in Unit 2 as well. But mesh analysis, node analysis, all those tools that we used in Unit 1 are just as available in Unit 3, except they're complex numbers. Nothing different if your calculator can do complex numbers. You know, certainly entering the stuff into the matrix, a little bit more care is required because you have more buttons to push, but it winds up being the same exact type of problems. So what are we looking at here? Well, we're already familiar with impedance. And so we have Laplace, we have our Z, R equals R, ZL equals SL, and if you don't remember this, it's probably a good idea to write it down.
Because then
Certainly has some bearing tonight.
certainly
And ZC equals 1 over SC.
okay.
What are we looking at here? Well, all this comes out of the Laplace analysis. And we didn't go into the theory behind Laplace. We didn't talk about the derivations of that table that you'll use this evening, whatever. But there is a comparable expression called Fourier analysis. So this is Laplace. And now we're going to look at Fourier. And essentially, Fourier and Laplace are related. Laplace, we have S. In Fourier, we have J omega. And those are equivalent as far as we're concerned. So any time in our Laplace analysis that we see J omega, or sorry, that we see S, we replace it with J omega for AC steady state. So the plus isn't going to go away on us. We're going to still use it to set up our expressions, and we'll use it for some other stuff when we look at filters. But in our AC steady state, you can write it yourself, of course, but ZR is still R. ZL is now J omega L. And ZC is 1 over J omega C. And we'll actually usually write this as J minus J over omega C. And that just comes out of the identity 1 over J equals minus J. That's an identity worth writing down. And it won't, but it could have some bearing on tonight. So, not really something you need, but if you feel like getting it in your crib sheet, can't hurt, I suppose. And so we look at these expressions, and we have this term omega, which is radial frequency. And we saw this in physics 2. Omega equals 2 pi f. So that's a relationship from physics 2. We have units, radians per second, where f, of course, is hertz, which is 1 over second. Seconds to the minus 1. And so 2 pi radians per second gives us radians per second. And so here's our term. Has everybody seen this before? Familiar? And so that's our expression. We can actually look at these and make some observational comments that are consistent with things we did in Unit 2. For example, as omega goes to 0, what is that equivalent to? So if the radial frequency is going to 0, what type of solution do we have? What does omega equals 0 correspond to? That's the DC steady state. The frequency going to 0, that's a constant. So that's the DC steady state. Well, if we think about this, as omega goes to 0, what is ZL? By observation, we substitute in omega equals 0. What's ZL? And how does that correspond to the DC steady state from Unit 2? We know the DC steady state of an inductor is what? A short circuit. So here it is, kind of verified mathematically. On the flip side, as omega goes to 0, what's our capacitor impedance? Well, 1 over 0 is a big number, arguably infinity. And so ZC goes to infinity, and is that consistent with the DC steady state of capacitors? A DC steady state, what is a capacitor? An open circuit. An open circuit is equivalent to infinite resistance, or now we're using this concept of infinite impedance. And so those are some of the characteristics we can look at. On the flip side, now with AC steady state, this is a sinusoidal problem. What if our frequency cranks way up? So we look at frequencies in the gigahertz or terahertz or beyond. Well, as frequencies increase, what happens to ZL? It becomes an open circuit. So as omega goes to infinity, or becomes large, then ZL goes to an open circuit, or becomes a very, very large number. And similarly, as omega goes large, what does ZC do? Well, capacitors become a short circuit. So this is something we haven't seen before. And we'll look at this again on Thursday. So these are all complex numbers now. And so if we think of a simple circuit, let's go and revisit our friend, the RC circuit. Let's make that 1K and this 10 to the minus 6 farads. And so what are we looking at now? Well, we need one more piece of information as we analyze these circuits. We need to know what our frequency is. And so I could say something like our V source equals 10 cosine 1000 t. And so our expression this is omega. So our form of our sources always take some form. Sources in AC steady state. We can be a little bit more general, Vs or Is, it doesn't matter. Equals some amplitude, omega t, plus some phase. That's the amplitude of the sine wave. And I'll say sine a lot. Yes, I know I wrote cosine, but what's the difference between sine and cosine? 90 degrees phase. We tend to say sinusoidal expressions, sine, even if we write cosine. Everything's sinusoidal. It's oscillating in the sinusoidal form. Here's our radial frequency. And here's a phase term. Typically, more often than not, but always, not always, typically phi equals 0. We'll use that mostly, but occasionally we won't. If we have more than one source that are out of phase, only one of them can be 0. And this is often our reference. So, and that'll come into play a little bit more, again, starting on Thursday when we dive into the details. So, there's our general expression, and here we have a 10-volt amplitude with a radial frequency of 1,000 and 0 phase. And so the question can be then, what's VC and what's VR? So as we look at this circuit, what's VC and what's VR? Well, we now want to look at the AC steady state equivalent circuit. And what does that look like? Well, I'm going to write this in a slightly unusual way. That's 10 angle 0. This means angle. Angle of 0 degrees. And you can do it in radians as well. Likewise, we can do something like 45. That's an angle of 45 degrees. Or, if you prefer, pi over 4. And right now, well, our resistor is still 1K, ZR equals 1K. And in this case, ZC now equals 1 over, I put J in the bottom again. Omega, well, omega is 10 to the 3. And our capacitor was 10 to the minus 6. And so this winds up being minus J 1K. You can verify that if you're so inclined. And so there's our new way of expressing things. We have a complex capacitance, or purely imaginary capacitance, and a real resistance. And if we ask, well, what's VC? Well, how are we going to find VC here? What's our friend in this particular circuit? Nothing's changed. It's still a voltage divider circuit. We can even write it symbolically the same way we could for Laplace, ZC over ZC plus ZR. There are no initial condition terms in AC steady state. So when we use ZC, ZR, and ZL, this is AC steady state. It's been a sinusoid since the beginning of time, minus infinity, so to speak. So there are no initial condition terms. With that said, when we use P-Spice, we have to convince P-Spice there are no initial condition terms. And so we'll have to be a little careful when we do that, because it does not do steady state problems for sinusoidal. It assumes everything turns on at t equals 0. So what are we looking at there? Well, there's our voltage divider expression that we've seen so many times before. And so we can write this out now. Well, ZC, that's minus J 1000 over minus J 1000 plus 1000. And I wrote this in this unusual form, 10 angle 0. And so before we journey onward and solve what our voltage across our capacitance is in this particular case, let's talk about this guy. There is some equivalence here. So everything in AC steady state oscillates at the same frequency. And we already kind of saw this a bit in Unit 2. So when we derive the differential expressions for a given circuit, no matter what component we looked at, when we looked at voltage and current, the differential expression was the same. The source side may have been different, but the differential expression was the same. We saw that for our RLC series parallel, and if we extended it beyond for any other type of circuit, the differential form is the same. And so that has the same implications here. If we have a source that oscillates at 1,000 radians per second, then the voltage across the capacitor is going to have the same oscillation frequency, radial frequency. The voltage across the resistor is going to be the same radial frequency, and same with the current. So everything's going to oscillate at the same frequency. If that's not the case, you have active components. So once you fire off a given frequency, everything has the same expression. So ultimately what we're going to wind up with then is VC is some VC naught cosine 1,000t plus some phi c, which sounds funny as I say it out loud. But an amplitude and a phase with the same frequency. And that's to be expected. And likewise, we can write VR. Some VR naught cosine 1,000t plus phi r. A different phase. Pretty sure it's going to be different. And a different amplitude, most likely. But the same oscillation frequency. Well, this is all trigonometric representation. Arguably, we could write this in a slightly different way. We could write this as VC equals VC naught. There's an amplitude. Well, I'm give myself a little bit more room. Equals VC naught e to the j 1,000t e to the j phi c. Right? Or if we want to write that out a little bit, we can just say VC naught e to the j 1,000t plus phi c. Because arguments and exponents that are multiplied together add. We've seen that before. Well, looking at this, what is this relative to this? So if we think about this with regard to Euler's law, we take that expression that we just wrote, VC naught, VC equals VC naught, come on, e to the j 1,000t plus the phi c. And we apply Euler's law, what do we get? Well, that's VC naught cosine 1,000t plus phi c plus j sine 1,000t plus phi c. Right? So that's Euler's law. We talked about that once before. Well, going back to our above expression, then here's our imaginary arguments. And here's the cosine term. What's the relationship between these two? Maybe a little subtle question. No one wants to hazard a guess? This is the real, oops, never draw that person. The real part of this is our measurable part. This is a mathematical representation, mathematical tool, phasor form. So we have this complex exponential, and again, we saw this with underdamped cases, but if you went through the trigonometry in the underdamped case, complex exponential would actually go away. Here it doesn't. So we can represent our voltages and currents using these complex exponentials, but when we make a measurement, we always get a real term. So our analysis, AC steady state, becomes what's called phasor analysis. And that's the complex analysis. But our measurable result it's always the real part of our complex expression. And the question may be, and it's a reasonable question, why do this then? I mean, why do this phasor complex analysis? Well, it's actually easier. It's much easier to do phasor analysis than it is to do trigonometric calculations in our circuits. And you'll see that. I think you'll agree with me. So what are we looking at here? Well, we have this complex expression. And to write this one more time, we have this VC equals VC naught. And I'm going to rewrite it slightly differently, e to the j omega t. Well, it was 1,000t, but in this case I left it as omega. Well, that's the same thing. I just reversed the exponential arguments. Remember, for everything we look at, this guy is the same. Our phase is different. We said that when we looked at the resistance, different phase, different amplitude. We could write VR, again, the same way. VR not e to the j phi r, but e to the j omega t. This term is the same for everything.
Yeah, it's the arrow.
Same for every expression. And because we want to save ink, we don't write it. That was kind of a joke. So what we do is our VC is VC naught angle VC. That's our new representation. That's how we write things. We know the amplitude, we know the phase, and the omega is given for everything. Amplitude and phase. That's everything we need for our circuit analysis. Once we know what omega is and we find amplitude and phase of each of our impedances, we don't need it anymore. It becomes implied, or we don't write it out. This corresponds directly to VC naught cosine omega t plus phi c. So this is our tool. But this guy is what we're looking at. This is the phasor form of voltage, impedance, whatever. We can write any of our complex terms in phasor form. So we have an amplitude and a phase. All of that's implied. All of that's given. And the omega is implied. So coming back to our little circuit here, we had this. Well, if we look at this, this winds up being, well, this is 1,000 angle minus 90 degrees. And that's square root of 2 times 1,000 angle minus 45 degrees times 10 angle 0. I skipped a bunch of math in there. And we'll cover this math kind of extensively, but does everybody somewhat agree with what I said? I suspect a number of you are trouble. So the thing to do here is to go and look at the real imaginary plot. Where is minus j 1,000 on the real imaginary plot? So if I look at that number, there's IM, there's real. Here's minus j 1,000 right down here, right? Well, what's the magnitude of this distance? 1,000. So there's my 1,000. What's my angle? That's a right angle, and it's minus 90 since it's down, or counterclockwise. Minus 90. And likewise, what did I do? What did I do with that guy? Again, there's 1,000. There's minus 1,000. There's my point. So what's the length of that line? Oops, I'm off. Square root of 2 times 1,000, as you just said. And what's my angle? Minus 45 degrees. So that's where I got those two terms. And so here's a nice, simple phasor expression for the voltage across the capacitor. And one of the beauties of the phasor form, we can treat magnitudes, or amplitudes if you feel like saying them as amplitudes, the same way we do any other math in multiplication and division. So what does this wind up being? Well, the 1,000 over 1,000 cancels. And so we're left with 10 over square root of 2. But let's write this going backwards a second. So we can cancel those thousands. We can rewrite this now as e to the j minus j pi over 2. Right? That's just going the other way. And now I'm using radians instead of 90s if you want. You could write it as minus 90. Over square root of 2, e to the minus j pi over 4. 10 e to the j 0. And I realize, again, this is a little bit fast. We'll do this in more repeatedly in next class, but hopefully you're somewhat following along. Well, looking at this, we can rewrite this now as 10 over square root of 2. Well, what's e to the minus j pi over 2, e to the j 0. What do we do with exponents that we multiply? We add them. E to the minus j pi over 4. So we can rewrite this one more time, 10 over square root of 2. So we add these. Well, pi over 2 plus 0 is, if we agree, pi over 2 minus pi over 2. E to the minus j pi over 2. And what do we do with exponents that we divide? We subtract. So we wind up with 10 over square root of 2, e to the minus j pi over 4. And now we can go back and write it the other way again. Go back to phasor form. 10 over square root of 2, angle minus pi over 4. Or if you're so inclined, minus 40, minus 45 degrees. So what does that mean for us? Well, here's an amplitude, here's a phase. What's VC? VC is 10 over square root of 2, going back to our original problem. Cosine 1000t minus pi over 4, or minus 90 degrees. Minus 45 degrees. And there would be our final expression. So we did all this with phasor analysis. We did it quickly. I realize, again, we'll hammer it into you Thursday and onward. And that's our new analysis. How do we get essentially the amplitude and the phase of our characteristics, of our voltages, of our currents? And we use these complex numbers with this phasor analysis. We build the circuit the same way. ZR, ZC, ZL, if we have ZL. We convert that now to a complex or imaginary term, as the case may be. Convert everything to a phasor expression, and we'll use those tools to find amplitudes and phases, to find our response. All right, so there's our introduction to phasor analysis. We'll do a team assignment that's not on this. And then once you're done with this, hand it in and you can take off. One more? Are you working with these guys?
I mean, what do you mean? I thought.
Is it working?
No, I mean, it says too many arguments, so I'm putting 3. Well, I have 3 arguments here. Local A, B, C. Yeah. Go on the Thursday by day. I got rid of the if statement because I want to do the complex. No, I don't know how to program it.
I guess I was there for the first. I guess I was the first person on there. So I got my email. I just like
Squeeze up.
they made me pay.
Oh, this one. Okay, can you say them quick? Because you had a negative sign by the A.
I had a negative sign by the A.
They were like where you were storing the A. So I don't know if that would affect it, but it still says too many arguments on the back.
I tried. My options is go back on
Still too many arguments. I mean, is that how you enter the arguments? Is that how you enter the arguments?
Yeah. Is that working?
Yeah. Am I supposed to not type it out?
Oh no, you're not supposed to do that. No, that's not how you enter the arguments.
Okay, how do I enter?
No, that was it.
Name of the program is Quad.
Yeah, okay.
You should also get one.
Yeah, there you go. So it was just quad and without any arguments.
Oh, and then you say A equals and
Yeah.
then B. Oh, that's annoying.
Wait, I might be able to fix it so that it does that. You want me to do that?
If you don't mind, I can.
Yeah.
I can do this.